Good day, everyone. Welcome back to Math 30-2. We've got a relatively short lesson today. What we're going to do is finish off with Lesson 2, which we got most of the way through yesterday. Lesson 2 deals with set theory, and we're going to continue with that today, and this starts on page 11. What we're going to be doing today is looking at two main ideas. One is called the intersection of sets, and one is called the union of sets. And we're also going to be looking at something else, which we'll get to when we get to. In order to make sense of this and to help you understand what an intersection is compared to a union, we're going to use some sets that were created in one of the examples from yesterday. I think it was on the previous page, which would have been page 10. And these were the three sets. It doesn't matter how they were defined, but I'll go through the definitions. These all had to do with non-negative single-digit numbers that were less than 10. Set E was the set of even numbers within that universal set. Set L was the set of numbers that were less than 7 in that universal set. And set O was the set of odd numbers less than 7 in that set. So we're going to use those three sets. Let's talk about an intersection of sets, first of all. The intersection of set A and set B, I'm just saying A and B in general. We'll get to the sets at the top of the page in a little bit. But the intersection of sets A and B is called a new set, A and B, and it's denoted, which means written as this. There's no special way for you to say this. You don't say A upside down funny U B. What you do, that part that I've highlighted in yellow, is you say that's the intersection of A and B. So you have to get used to that notation. What is this new set, which is the intersection of A and B? It is the set of elements that are members of both sets A and B. This is something we actually did. We did problems in the very first lesson in this unit. I can't remember the exact details, but we might have done a question where we had a set of even numbers, say less than 20, and a set of prime numbers less than 20. And perhaps what we had to do was find out a new set, which was the list of even and prime. What we were really doing was finding the intersection of those sets. And I'll get to why we use the word intersection in a bit. But basically, the intersection is written the way it is. It means whatever is in both of the sets is in the new intersection set. And as an illustration here, what is the intersection of sets E and L? Well, we would write E. We would write the intersection of E and L is equal to, and we would look at set E and set L and identify items that are in both of the sets. So there is a 0 and a 0 in each set, which means 0 will be in the intersection. There is a 2 and a 2, a 4 and a 4. There is a 6 and there is a 6. And there is an 8, but there's no 8 in the larger set or in set L. So what is the intersection of E and L? It is the set that includes the following elements: 0, 2, 4, and 6. And we're done. That's the basic idea behind an intersection. But let me explain to you why it's called an intersection. And I don't need to do this, everybody, because this is going to be in a coming up lesson. But I think it might be helpful now and later for you to see it. What I'm going to do is construct a diagram, which is really just a model of these two sets and their relation to each other. Let's call the set on the left E, and the set on the right L. And if I start putting the elements in each of the sets, remember E was even, so that was 2, 4, 6, and 8, and also 0. I can put the 8 here, but when I write down the 0, I'm going to put it in this overlap. And the reason is 0 is an element of E and an element of L. Don't forget, the intersection was 0, 2, 4, and 6 because those elements are common to both sets. So I can put a 2 here, a 4 here, and a 6 here. And if you now focus your attention on set E contains all of the elements of set E. It contains 0, 2, 4, 6, and 8. Now we focus on L. What was set L? It was 0 through 6. So if I put in those other elements of set L, I already have 0, 2, 4, 6. I don't have the 1. I don't have the 1. I don't have the 3. I don't have the 5. Let's see, 0, 1, 2, 3, 4, 5, 6. Now if I focus my attention on set L contains all of the elements of set L. They're within that circle. But there's an overlap, and this overlap is the intersection. This is the intersection of those two sets. It's where they cross, it's where they intersect. And that's why we call it an intersection. Now again, I don't have to do this now because we will learn it officially later. But my experience has been, I guess it's not A, my experience has been if students see it now, it's E intersecting with L. If students see it now, they're likely to be more successful. So when you have E and L, it's the intersection of E and L. It's graphically, and by graphically I don't mean a XY grid, I mean a graphic. It's graphically represented to you this way, and that's why it's called the intersection. Let's talk about the union now of sets. Well, the union of sets A and B is called A or B, and that word or is the same thing we saw previous in this unit, which means it's anything in A or anything in B or anything in both. And it's written this way. And again, there's no funny way of reading this. You don't say A, U, B. You say the union of A and B. And it's the set of elements that are members of either set A or set B or both, because in math we use the inclusive use of the word or. We're asked to do something here, use appropriate notation to write the union of sets E and L. Well, the union of sets E and L will be a new set that contains an element if it's in E, or an element if it's in L, or an element if it's in both. And you're given a hint here, do not write the same element twice. So 0 is represented in those sets, in both sets. But we include it because it's in at least one of them. We include 1 because it's in a set. We include 2 because it's in a set. 3, 4, 5, 6, and 8. So why are we including 8? Because it is in set E. Why are we including 1? Because it is in set L. Why are we including a number like 2? Because it's in both sets. It has to be in one or the other or both. Now, if I go back to my diagram, this what we call a Venn diagram, and I just adjust it slightly, let me get back to where I want to be. We're talking now about the union of these sets, and that means this is not what we're interested in. This is not what we're interested in, but it's still the same two sets. So this diagram still tells us how these sets connect to each other. if I want to represent visually the union of E and L, it's this. It's everything. And there's so much we could talk about with Venn diagrams, but it doesn't matter at this point. Even if those circles were all over the place or separate from each other, you would still be looking at everything they cover. So if you compare these two now, just in preparation for later, not really worrying about right now, this is the intersection of two sets, and this is the union of two sets. Everything that's highlighted here would be an element in the union. Everything that's highlighted here would be an element in the intersection. So those are the two main things. I also want to talk with you about what are called disjoint sets. And well, I'll go back. I just had a thought, but I want to save it for later. What is a disjoint set? A disjoint set, or a pair of disjoint sets rather, are two sets that have nothing in common. In other words, the intersection is the empty set. Like, think about this. If I had 2, 3, and 4 in a set, and then 5, 6, and 7 in another set, and I asked you, what is, let's call this set A and set B. And I said, what is the intersection of A and B? The answer is going to be, it's the empty set. Why is it the empty set? Because there's nothing in common with A and B. There's no element in A that's also in B. So if two sets are disjoint, they would have no element in common. The intersection would be the empty set. By the way, the union of these sets, even though they're disjoint, would be 2, 3, 4, 5, 6, 7. And I want to talk about that right now in terms of my Venn diagrams. And then we have a little question to do here. If we were dealing with those two sets, and they are disjoint, then the simple fact of the matter is there's no connection between them on paper. They don't overlap in any way. Now, be very careful here. They don't overlap because they're disjoint. Don't read anything else into it. If they are disjoint, they will look like this. So what we have is 2, 3, and 4 over here, 5, 6, and 7 over here. And again, I'm getting ahead of myself because this is tomorrow's material, or coming down the pipe anyway. It's not officially part of this lesson. So what is the overlap? There is no overlap. What is everything shaded? Everything shaded, which is the union, doesn't require an overlap. Again, I'm trying to draw connections between what we're talking about right now and what you're going to see later on. Getting back to our discussion and your note pack, not note package, your workbook, which two sets above are disjoint? Well, L and O are not disjoint because they have something in common. L has a 1 and O has a 1. So it's not L and O. Is it L and E? Well, no, it's not L and E because they have something in common. What it is E is disjoint from O, and we can just write that as an answer, and then I want to summarize this. E and O are disjoint. The reason is there's no overlap. And by the way, that means that E intersection O is the empty set. And I'm going to give everybody a minute to think about why the intersection of O and the intersection of E must be the empty set. These two things go hand in hand. Any two sets that are disjoint have no intersection because of this. All right. We have one example now. It's class example 3 in this lesson. We're looking at now a different set of sets. This goes way back to, I don't remember the context, but the universal set was numbers that were natural less than 20. Set A was the set of numbers that were less than 20 within that universal set, divisible by 3. And I changed the font size to make things fit. This is set A. This is set B, which were multiples of 5, or numbers that were divisible by 5. And set C was this, which were multiples of 6, or numbers that were divisible by 6. And we're going to answer some questions now. List the elements of the following sets. So what do we have? The intersection of A and B. What elements are in the intersection? Well, they have to be elements that are in A and in B. So when you take a look at elements that are in both A and B, 6 is in both, 12 is in both, and 18 is in both. Whoops, my mistake. Sorry about that. A and B, not A and C. 6 is not in both. So let's start with 3 in the yellow set. 3 is not in the blue set. 6 is in the yellow but not in the blue. 9 is in the yellow but not in the blue. 15 is in both. And that's the only number. This is the only number or element that is in both set A and set B. Sorry for that. It's A and B. So the intersection of A and B is this set. All right, what about the union of A and B? Well, that's easy because the union of A and B means A or B, and that means it's anything in A or B. So essentially, it's everything. So we have a 3. I'm just going to put them in numerical order. We have a 3, we have a 5, we have a 6. There's no 7, there's no 8, there is a 9 and a 10. There's a 12, a 15, and an 18. And a lot of numbers swirling around, so I just want to take a minute and double check my work. I'm just going to move this a bit. 3, 6, 9, 12, 18. We also have 5, 10, and 15. Looks okay. So what about the intersection of not A and B? So this is not A and B. This is what this means. So I think it's good advice to write down what not A is. And I'm just going to squeeze it in at the top of the screen here. Not A are all of the numbers from the universal set that are not in A. 1, 2, 3 is in there. 4, 5, 6 is in there. 7, 8. 9 is in there. 11, 12. Pardon me. 10, 11, 12 is in there, 13, 14, 15 is in there, 16, 17, and 19. We'll double check that. 1, 2, 4, 5, 7, 8, 10, 11, 13, 14, 16, 17, and 19. At the top of the screen is not A. So we are looking now for anything that is in not A, so in this, and in B. So I would start with the smaller set. Look at the number 5, which is in B. Is 5 also in not A? Yes, it is. That means 5 is part of the set of the complement of A and B. The next item in the smaller set is 10. Is 10 also in not A? Yes, it is. The next item is 15. Is 15 in not A? No. So that's it. 10 and 15. Let's take a look at number B now, or letter B in this example. Write a set equivalent to B and C. So I will very often write or say B and C, and then sometimes I will say the intersection of B and C. So what is the intersection of B and C? Here's B, and here's C. Is there anything that is in both? No. There's nothing that's in both. These two sets are disjoint, which means that the intersection of B and C is the empty set. What about the union of A and C? Well, the union of A and C is all of the items, whether they are in A or C or both, right? This is A or C. Well, 3 is in A or C. So is 6, so is 9, so is 12, so is 15, so is 18. And let me highlight those numbers for you, because I want to make an important point. This must be in the union because it's in one of the sets. So must this, and this. All of these numbers are in the union of A and C. But since C is entirely enclosed by A, the union of these two is still going to be 3, 6, 9, 12, 15, and 18. In other words, the union of A and C, the union of A with C, is simply set A. And if you were looking for an interesting kind of thing here, and I think it is interesting, it hopefully will demonstrate a really good understanding at some point in your head about what's going on. The only way this can happen with A and C, I guess I'll put them so you can see it, is the following. The only way this kind of thing can happen, where the union of two sets is one of the sets, is if the larger of the set encloses the smaller of the sets. So set C is entirely within set A. So the union is just set A because it's got set C covered. What about A and C? A and C. Well, that means it has to be in both. What elements are in both sets A and C? Well, this 6 is. the 6 is, the 12 is, and the 18 is. Huh. Well, that's interesting. What we've got going on now is that the intersection of the two can be described as C. I mean, look at what the intersection is. It's 6, 12, and 18, which is C. That means the intersection of A and C is C. And I think you might be able to make sense of that because where these things overlap in our Venn diagram, where these things overlap in the intersection, it's all about overlap, is right here. What do we shade in for this one where there's a union? We shade in everything. So in the large yellow shading, we've just shaded in A. In the small yellow shading, we've just shaded in C. We got one more. If we introduce now a new set, D, which is 2, 4, 6, 8, 10, 12, 14, 16, 18, what is the intersection of the union of B with D? Well, I think it will be helpful for us to write down what the union of B with D is. That's a list of everything in B and D. Everything. It could be in B or D or both. So what do we have? 2. We're looking, or I'm looking anyway, at D and B. This is what I'm looking at for the union of B and D. 2, there's no 3. There is a 4. Is there a 5? Yes. Is there a 6? Yes. A 7? No. An 8? Yes. No 9. There's a 10. No 11. There's a 12. No 13. There's a 14. There is a 15. There is a 16. And there is an 18. Now I'm going to double check that. 5, 10, and 15 are in there. 2, 4, 6, 8, 10, 12, 14, 16, 18. It's in there. We're missing a 3, and that's good. We're missing a 1, that's good. We're missing a 7. We're missing a 9, an 11, a 13, and a 17. I'm just looking at this in a lot of different ways to make sure I have them all. So this is B in union with D. Now we want that, we want this and this to intersect. All right, in part C, part 1, it says the intersection of A, which is this, with the union of B and D, which is at the top. So what's in common? What's the intersection? Not 3, not 4, not 5. We have a 6. So this will be the intersection of A with the union of B and D will be a set that includes the number 6. Does it include 9? No, it includes 12. Again, I want to start with the smaller set. It will make things easier to eliminate things. 3 is in the smaller but not in the bigger. 6 is in both. 9 is in the smaller but not the bigger. 12 is in both. 15 is in both. 18 is in both. So now I'll double check that. 6 is in both, 12 is in both, 15 is in both, 9 is not, and 18 is. So that's the intersection of A with the union between B and D. It's simple, but it's hard on the brain, I think is the best way to put it. What about the union of A and B with D? So the union of A and B with D. Well, that means it's going to be anything in D and anything that's in A and B. So I am going to, up here, just off on the side, figure out what the intersection of A and B is. What do those two sets have in common? What I am figuring out, everybody, is what this is. They don't share 3 in common. They don't share 6, 9, 12, 15 is the only thing. In fact, had I been more on my toes, I think we already figured this out in a previous question. Anyway, the intersection of A and B is 15, so now this set will be equal to anything that is in A and B or in D. Well, all we have to do is add that 15 to D and we've got our answer. 2, 4, 6, 8, 10, 12, 14, add in that 15, 16, and 18. Remember that union symbol means or, which means you just list everything, whether it's in one of the sets or the other or both. And one of the sets here was this set, which we had to figure out first over here. Not A intersecting with not B, and we want not the whole thing. Oh my goodness. Well, I'm going to have to go to a new page for this. Okay, here we go. This is for part C, part 3. I think your best line of attack here, and with Venn diagrams you might be able to sort it out in a cleaner way, but that's for another day. I think we should write down what not A is, what the complement of A is. Remember, the universal set goes from 1 to 19, so the complement of A will be any of those numbers except for what's in A, which will be 1, 2, 4, 5. I'm looking up here. This is my eyeball, and I'm just pulling all of those out of the universal set. We need 7 and 8. We need 10 and 11. We need 13 and 14 and 16 and 17 and 19. So now, and again, I have a feeling we've done this already somewhere else, but I'm going to double check. 1, 2, 4, 5, 7, 8, 10, 11, 13, 14, 16, 17, and 19. That's not A. What is not B? What is the complement of B? Well, B is 5, 10, and 15. So that means not B is all of the numbers except for 5, 10, and 15. It's 1, 2, 3, 4, 6, 7, 8, 9, 10. Nope, not 10. 11, 12, 13, 14, not 15, 16, 17, 18, 19. This is not B. So now, what is the intersection of the complement of A and the complement of B? Well, it's anything that's in both lists, which would be 1 and 2. 4 is in both lists. 5 is not. 6 is not. Both 7 and 8 are. 9 is not. 10 is not. 11 is. 13 is. 14 is. 16 is. 17 is. and 19 is. And again, I think it's a good idea to double check things here. I'm looking for numbers that are common to A prime and B prime, because that will be the intersection of A prime and B prime. 1, 2, 4, 7, 8, not 9, not 10, 11, 13, 14, 16, 17, and 19. So if that is the intersection of the complements of A and B, so the question becomes, what is in the universal set but not in here? Well, a 3, a 5, a 6, a 9, and a 10. 12 is not in there. 13, 14 are. 15 is not in there. 16 and 17 are in there. 18 is not, and 19 is in there. Just do a final count here. And it looks good. So this is our answer. That's it for this lesson. Not a lot of big ideas, other than the fact that this means what we call the intersection, and it means A and B. This, which is called the union, which means A or B, and you should know from previous lessons that A or B means A or B or both. And then, of course, disjoint sets where the intersection is the empty set. This means we're talking about disjoint, and there is no overlap. Hope that made sense to you. You can get to work now on questions 8 through 14, which is the remainder of the problem practice set in your workbook for lesson 2. We'll talk to you later.